Good afternoon, students. So yesterday we did one theorem. Now let us do remaining three theorems. No, yesterday I stopped at this f plus g, f minus g. No, so let us finish off that first. Then we'll go for, once again I repeat the same question. Then we'll go for theorems, and today theorems will be finished. Is it clear? Right. See here. So yesterday the question was, if f is equal to 4, 5, if f is 4, 5, 5, 6, 6, minus 4, and g is equal to 4, minus 4, 6, 5, and 8, 5, right? Then find first bit f plus g, second bit f minus g, the third bit is 2f plus 4g, your fourth bit is f plus 4, your fifth bit is fg, your sixth bit f by g, your seventh bit mod f, your eighth bit root f, ninth bit f square, 10th bit f cube. Is it clear? Now let us see the solution. Given f equal to 4, 5, 5, 6, 6, minus 4. So g is equal to 4, minus 4, 6, 5, 8, 5. Right? Now here domain of f. Domain means first elements of the ordered pairs. 4, 5, 6. And domain of G, that is 4, 6, 8. First elements of the ordered pairs are called domains. Now I am going to find the domain of f intersection G, because in the given question I am having f plus g, f minus g. There you should take the common domain. So f intersection G is nothing but, what is your common domain here? That is 4, 6, right? Which is nothing but A intersection B. It is like A intersection B. Okay. What was your first bit? F plus G, correct? F plus G, that is equal to common domain I am asking. So that is nothing but 4, correct? No? Common domain is 4, f of 4 plus g of 4. So that is 5 minus 4, next 6. Then I should go for f of 6, f of 6 plus g of 6, right? Okay, instead of doing directly, let us write. I will show you. So f plus g is your, that is f plus g of 4. That is f of 4 plus g of 4. And what is your f of 4 according to the given question? 5. G of 4 is 5. Five plus of minus 4, that is 1. Next, f plus g of 6, because 4 and 6 is your common elements, right? And that is f of 6 plus g of 6. What is your f of 6? Your f of 6 is minus 4 and g of 6 is 5. It is nothing but 1. So f plus g is nothing but 4, 1, 6, 1. Okay. And from here onwards, let us do little bit directly. that is f minus g, your second bit, correct? Again, f minus g means what I am having? Common elements, 4. F of 4 is 5 minus of minus 4. And what is next? 6. What is your common domain? 6. So then f of 6 plus g of 6. What is your f of 6? Just now we did that. Minus 4. Then g of 6 is minus 5. Correct now? That is nothing but 4 comma 9. And this is 6 comma minus 9. 6 comma minus 9. Next, third bit. What was your third bit? It was 2f plus 4g. Correct, no? What is that ordered pairs? First, again, I should take 4. Right? So let us do this separately. 2f plus 4g of 4. That is nothing but 2f of 4 plus 4g of 4. What is 2 into what is your f of 4? It was your f of 4 is 5 plus 4 into minus 4. On simplification of this, what I'm going to get? 5 2s are 10 minus 16. What I'm getting is minus 6. Is it clear? Similarly, I should go for 2f plus 4g of 6. That is 2f of 6 plus 4g of 6. 2 into what is that? F of 6 minus 4 and g of 6 is how much? 5. G of 6 is 5. So what I'm going to get there? Minus 8 plus 5 4s are 20 is 12. Now, therefore, here f, okay. Here only I will write that part. So 4 comma minus 6 and 6 comma 12. This is your answer for 2f plus 4g. Is it clear? Next, f plus 4 I am having. F plus 4 means directly it is all only single function I am having f. Means all everything you are going to take. Means the complete domain of f. That is nothing but 4 comma 5 plus 4. Next, 5 comma 6 plus 4. Next, 6 comma minus 4 plus 4. For example, I will show you f plus 4 of 4. That is f of 4 plus 4 only. Don't write 4 into 4, 16. Is it clear? That is a mistake. This is like function x. So f of x plus 4 as it is. What is f of 4 actually? 5 plus 4. This is how you are going to get 9. Is it clear? For your understanding purpose, I showed you one. Like that, f plus of 5 also you will do. That is f of 5 plus 4 again. Right? What is f of 5? 6 plus 4. It becomes 10. F plus 4 of 6. That is f of 6 plus 4 only. Don't write 4 6 are 24. That is a mistake. Is it clear? So what is your f of 6? Your f of 6 is minus 4 plus 4. What I got is 0. So that is nothing but your f plus 4 elements will be 4 comma 9, 5 comma 10 and 6 comma 0. 6 comma 0. Is it clear? Again, fifth bit. Fifth bit, what I'm having here? Fg. Fg means it is like Fg of x. That is f of x into g of x. So Fg. Again, I'm having two functions. Whenever I'm having two functions, I should consider the domain of two functions, common domain. So 4 and 6. That is f of 4 into g of 4. What is your f of 4? It was 5 into minus 4 minus 20. Fg of 6. That is f of 6 into g of 6. What is f of 6? Minus 4 into 5 minus 20. So Fg is equal to so that is 4 comma minus 20, 6 comma minus 20. Is it clear? So whenever I'm having two functions, I will take the common domain as I said. So what is the common domain for two functions? F intersection G, two functions. So this is your common domain. 4 comma 6. So that's why wherever I'm having f and g combination, either it can be plus minus product, I'm going to take only 4 and 6. Next, f by g. F by g is f by g of x is f of x by g of x. Like this, your definition is. So f by g of 4, f of 4 by g of 4. What is f of 4? Your f of 4 is 5. What is g of 4? Minus 4. And f by g of 6. What is that? It is f of 6 by g of 6 minus 4 by 5. Therefore, your f by g ordered pairs. For 4, I got minus 5 by 4. And for 6, I got minus 4 by 5. Is it clear? So, this is how you are going to do. Next, mod fg. That is your 7th bit I am talking about. Mod f of x is nothing but mod of f of x. What is the definition? Mod f of x is nothing but mod of f of x. Okay. All right. Let us start now. Again, single function. Single function means I should take mod f of 4. That is mod of 5. That is 5 itself. Mod f of 5. That is mod of f of 5. I should take the complete domain of f. So domain of f is 4, 5, and 6. Is it clear? That is mod 6 is 6. Next, mod f of 6. That is f of 6. Mod, what is f of 6? Is minus 4, that is plus 4. So mod f ordered pairs will be 4 comma 5, 6 comma 6, sorry, 5 comma 6 and 6 comma 4. 4 comma 5, 5 comma 6, 6 comma 4. What is your 8th bit? Root f. Root f of x is nothing but the root of f of x. Is it clear? So let us go for root f of 4. That is root f of 4. That is root 5. Okay. Next, root f of 5. That is root f of 5. That what I am getting? Root f of 5 is 6. And root f of 6. Right? That is root f of 6. That is root minus 4, which is not possible. Why it is not possible? Inside the root, I cannot get negative value. Is it clear? So your root f, I will have 4 comma root 5 and 5 comma root 6. Next, 9th one, f square of x is nothing but f of x whole square. So f square of 4, that is f square of 4, that is f of 4 whole square according to the definition. What is f of 4? 5 square, that is 25. F square of 5, f of 5 whole square. What is your f of 5? 6 square, that is 36. Next, f square of 6, that is f of 6 whole square. What is f of 6? Is minus 4 whole square, that is 16. So f square is equal to 4 comma 25, 5 comma 36, 6 comma 16. These are your ordered pairs. 4 comma 25, 5 comma 36, 6 comma 16. Last bit, that is the 10th bit, f cube of x. That is f of x whole cube. That is the definition. So f cube, again single function. Whenever you find single function, you are going to take domain elements of that particular function. So yeah, single function is f. So f cube of 4, that is f of 4, its whole cube. What is f of 4? 5 cube, 125. F cube of 5, f of 5, whole cube. F of 5 is nothing but 6 cube 216. F cube of minus 6. F of minus 6 whole cube. What is f of minus 6? Minus 64. So your f cube ordered pairs will be 4 comma 125, 5 comma 216, minus 6 comma minus 64. Two one six minus 6 comma minus 64. That's all. Is it clear? Very important one. Okay. Very important means in 7 marks, he was asking like 4 bits, 5 bits among these 10 bits. Is it clear? Right. Now let us go for theorem. Second theorem. I will finish off all theorems today. Theorem 2, what it says? If F is mapping from A to B and G is mapping from B to C are bijections. Are bijections, then prove that, very important, then prove that G circle F whole inverse is F inverse circle G inverse. Then prove that G circle F whole inverse is F inverse circle G inverse. Given F is mapping from A to B, G is mapping from B to C are bijections. If they are bijections means what? That implies F comma G are both 1, 1 and on 2. That implies F inverse comma G inverse exist. If they are bijections, then F inverse comma G inverse exist. Therefore, F inverse is mapping from B to A and G inverse is mapping from C. The G inverse is mapping from C to B are also bijections. Is it clear? Are also bijections. Now let us write the composite function F inverse circle G inverse. Your F inverse circle G inverse is mapping from the composite function. Your second function domain will be the domain of the composite function, and first function's codomain is the codomain of the composite function. And now G circle F is also mapping from A to C is also bijection. Is also bijection. If at all it is, just now we proved in first theorem, no, yesterday we proved in first theorem that G circle F mapping from A to C is also bijection. Is it clear? G circle F is mapping from A to C is also bijection. Means that implies G circle F whole inverse exist. I mean G circle F whole inverse exist. Therefore, G circle F whole inverse is mapping from C to A is also bijection. Okay. Now see here. F is mapping from A to B, G is mapping from B to C are bijections. F and G are both 1, 1 and on 2. That implies F inverse and G inverse exist. Now what is F inverse? B to A. And what is G inverse? C to B are also bijections. Now F inverse circle G inverse is mapping from where to where? C to A. Is it clear? C to A. Okay. F inverse is mapping from B to A and G inverse is mapping from C to B are also bijections. Now write the composite function. F inverse circle G inverse. That will become C to A. Okay. That is also a bijection function. Is a bijection because I don't know, is there? bijection. Right. Next. Now, G circle F is mapping from A to C is also bijection based on your first theorem. That implies G circle F whole inverse exists. Whenever any function is a bijection, means if it is both 1, 1 and on 2. So definitely your G circle F whole inverse exists. It is a bijection. Whenever it is a bijection, inverse exists. Now G circle F whole inverse is mapping from C to A are also bijection. So therefore, your F inverse circle G inverse and G circle F whole inverse. This statement you have to write compulsory. Are defined on same domain and are defined on same domain and codomain. Are defined on inverse circle G inverse and G circle F whole inverse are defined on same domain and codomain. Now, what he has given, F is mapping from A to B is a bijection. Correct? Bijection means for every A belongs to A, then your F of A, its image equal to B. And A equal to, I can write it as F inverse of B. Why? Because it's a bijection, inverse exists. Inverse exists means what? F, you bring it to this side, it becomes F inverse. Next. G is mapping from P to C is a bijection, it's given. These two things you have to write compulsory. Now for every B belongs to B, then its image G of B will be equal to C because C set no, right? Means B equal to, I can write it as G inverse of C. So students, keep this thing in your mind, this part and this part. Okay, right, this also. Okay, now. Okay, now G circle F is mapping from A to C is a bijection. It is given, correct? Means for every A belongs to A, then its image I am talking about. For every A belongs to A, now its image. Then G circle F of A, it belongs to C. Okay. Now I am going to take G circle F of A. That I will write it as G of F of A. That is G of, what is F of A? B. What is G of B? C. C. G circle F of A, I got it as C. Since it is a bijection, A equal to G circle F inverse. This I will put it as 1. Now you take F inverse circle G inverse also. Mapping from where to where? C to A. Means for every C belongs to domain element you take, then its image, that is F inverse circle G inverse of C. That is F inverse of G inverse of C. That is F inverse of, what is G inverse of C? B. What is F inverse of B? A. So F inverse circle G inverse. This I will put it as 2. Now from 1 and 2, here F inverse circle G inverse is equal to G circle F whole inverse. So from 1 and 2, here F circle, yes or no? Because A and A are same, no? Both sides. Your A, here A, see here. This A, and this A, both are same. Now equate this and this. That only we did. So F inverse circle G inverse is equal to G circle F whole inverse. Very important theorem. Once again, you can have a look. So I told you already this part, G circle F whole inverse exists. Then G circle F whole inverse is mapping from C to A is also bijection. Now F inverse circle G inverse and G circle F whole inverse are defined on same domain and codomain. Now F is mapping from A to B is a bijection. And for every A belongs to A, your F of A equal to B. A is equal to F inverse of B. Then G circle F is mapping from A to C is a bijection. For every A belongs to A, your G circle f of A belongs to C. Now, these two you have to define separately first. Is it clear? This part compulsory, right? Here only. Next, G circle f of A is nothing but G of f of A. Your f of A is nothing but B. Your G of B is nothing but C. Is it clear? This is about your second theorem. Now let us do third theorem. Let Fp is mapping from A to B. Ia and Ib are identity functions. Ia and Ib are identity functions on capital A and capital B. Then prove that F circle Ia is equal to Ib circle F. This we are going to prove, correct? Now, see the proof. What he has given is given F is mapping from A to B, and Ia is a mapping from A to A, and Ib is mapping from B to B, are identity functions. Are identity functions. Now, F is mapping from A to B, I said. Now, I'm going to write the composite function. Which composite function? This composite function I am going to write. That is the composite function I wrote. That is F circle Ia. Now, F circle Ia is mapping from where to where? How to write the domain and codomain of a composite function? In that composite function, what is the second function? Ia. What is the domain of Ia? Is the domain of the composite function. Mapping to what is our first function? In always composite function, the second or the last function domain will be the domain of the composite function, and the first function's codomain. What is the first function codomain again? B. That will be the codomain of the composite function. Is it clear? So therefore, your F circle Ia and F are defined on same domain and codomain. They are defined on same domain and codomain. Correct? No? Okay. Now let us see. Now F circle Ia is mapping from A to B. Therefore, for every A belongs to A, then your F circle Ia of A, it belongs to B. Let us prove that part now. So F circle Ia of A, that is F of Ia of A. But what is Ia of A? Identity function. A only I get. Means that is nothing but F of A. Yeah, correct? No? So therefore, F circle Ia of A, I got F of A. Therefore, F circle Ia is equal to F. This is, we proved it. Next. Now, F is mapping from A to B, and IB is mapping from B to B. Correct? No? Now let us see what I have to show. IB circle F. Which composite function I should write? IB circle F composite function, that is mapping from. In this IB circle F composite function, what is the second function? F. What is the domain of F? What is the domain of F? A. What is the domain of F? It is A. 2. What is the codomain of IB? It's P. Right? So therefore, again, IB circle F and F are defined on same domain and codomain. are defined on same domain and defined on same domain and codomain. Is it clear? Now, again, IB circle F is mapping from again A to B. Now, for every IB circle F is mapping from A to B. Now, for every A belongs to A, then its image IB circle F of A, which I am going to write it as IB of F of A. But what is F of A? It's B, because your F of A, it is nothing but B, because F is mapping from A to B, it's already given. But IB of B is B. Why? Because it's an identity function. But what is B? F of A. What is B? F of A. So IB circle F of A, I got. So therefore, IB circle F equal to F. This is your first one. This is your second one from 1 and 2. From 1 and 2, F circle IA equal to F, that is equal to IB circle F. F circle IA is equal to F, that is equal to IB circle F. Yeah. Still any doubts? You can ask me, because F of A, your F of A is nothing but B, and your B is nothing but again IB of B is B itself. And what is B? F of A only. Write down here if you want. Since your F of A equal to B, because F is a function from A to B. Is it clear? Right, that's it. Yeah, you can have a look. Still, if having any doubts, anything, I mean, go through the ones. I hope you understood. Fourth one, let F is mapping from A to B. These are the four theorems which are important. Be a bijection. Then prove that. F circle F inverse is IA, and F inverse circle F is IB. And prove that F circle F inverse is IA, and F circle, sir. Then F circle F is equal to IB. Now see the proof. See the proof, everybody. This is also very important and easy. What he has given is F is mapping from A to B is a bijection, it seems. Whenever it is a bijection, that implies F inverse exists. Therefore, your F inverse is mapping from where to where? B to A is a bijection. Correct, no? Now, what he has given, IA is mapping from A to A, and IB is mapping from B to B are identity functions. Are identity functions. Okay. Right? Now, let us, so F is mapping from A to B is a bijection. Let us define this and keep it aside. Means for every A belongs to A, then your F of A is equal to B. Then A equal to what I can write it as F inverse of B. Keep this part here because we are going to use this part. Is it clear? Right. Now let us go for next page. So once again, I'm repeating. Here F is mapping from A to B is a bijection. That implies F inverse exists. Means F inverse is mapping from B to A is a bijection. Then IA is mapping from A to A and IB is mapping from B to B are also identity functions. So F is mapping from A to B is a bijection. For every A belongs to A, then F of A equal to B. Then A is equal to F inverse of B. A is equal to F inverse of B. F of A equal to B, then A will be F inverse of B. Why? Because F is a bijection, F inverse exists. Now, let us define F circle F. That only now what is asking? F inverse circle F. Now, that is mapping from, now this composite function, second function's domain is A. Second function's domain is A. Is mapping from F inverse codomain is again A. Correct? Therefore, your F inverse and F and IA are defined on same domain and codomain. Are defined on same domain and codomain. Now, I'm going to take F inverse circle F mapping from A to A. Means for every A belongs to A, then your F inverse F of A, its image, that I'm going to write it as F inverse of F of A. Now F inverse of, but what is F of A? Here I wrote already. Your F of A is B. What is your F of A? F of A is B. And what is F inverse of B? What is F inverse of B? A. Correct? That is A. But what is A? I can write it as IA of A. Why? Because identity function. Identity function. Is it clear? So F inverse circle F of A, I got IA of A. Means therefore F inverse circle F is IA. I proved one part. Next, what I have to show? F circle F inverse. But first, let us define this function from which set to which set. So F circle F inverse. What is F circle F inverse? Composite functions. Second function F inverse. F inverse domain is B. If you want, you can check it. F inverse domain is what? B. F inverse domain is B. Mapping to F codomain is again B. Right? Now therefore, F circle F inverse and IB are defined on same domain and codomain. Again, they are defined on the same domain and codomain. Now, F circle F inverse is mapping from B to B. Means for every B belongs to B, then its image F circle F inverse of B. That is F of F inverse of B. That is F of, what is F inverse of B? A. What is F of A? B. B, I can write it as IB of B. Is it clear? Therefore, F circle F inverse is IB. That's all. So, with this, only 4 theorems are important. And if at all is not giving theorem, then we will go for some other question. Is it clear? It depends. So most 4 important theorems, 99% is not going beyond these theorems. And these are very, very important questions. Is it clear? Yeah. Sometimes is asking in 7 mark this question also. That is, yeah, I hope you understood. This simplification, see this properly, right? F inverse circle F of A, F inverse of F of A. What is F of A? B. How? F of A is B. F is mapping from A to B. Is it clear? And F inverse of B is again A. Because F of A equal to B, then A is equal to F inverse of D, since it's a inverse function exists, because they are bijection. It's given in the statement itself. Is it clear? Next. This is also important. F is given as 1 comma A, 2 comma C, 4 comma D, 3 comma B. And your G inverse is given as 2 comma A, 4 comma B, 1 comma C, 3 comma D. Now, see, either F is given, G is given, whatever it is given. I want 4 things: F, G, F inverse, and G inverse. So let us find F inverse first. That is, inverse means your ordered pairs. Like what I said, F is mapping from A to B, F inverse is mapping from B to A. So A comma 1. This is C comma 2. This is D comma 4. Reverse the ordered pair, that's all. Right? Now I want here G. A comma 2. Right? B comma 4. C comma 1. D comma 3. Okay. Now what is asking us to show that? Show that the theorem which we proved just now. G circle F whole inverse is F inverse circle G inverse. And these are the given things what he has. Now let us find first G circle F. Now in G circle F, what is the second function F? Whose domain is what? 1. So 1. 1 is mapped to A. Correct, no? But A is mapped to what? 2. So 1 comma 2. You are going to write like this. Next, 2 is mapped to C. C, check your F. 1 is mapped to A, and in G, A is mapped to 2. So 1 comma 2. Next, 2 is mapped to C, and C is mapped to what? 1. So 2 comma 1. 4 is mapped to D, and D is mapped to 3. So 4 comma 3. And 3 is mapped to B, and B is mapped to 4. So 3 comma 4. See, I got G circle F. It's a composite function. The mappings. Is it clear? Now, G circle F whole inverse I do. Yeah, this was asked in 7 mark once. Easy question, 4-5 lines, right? So that is 2 comma 1, 1 comma 2, 3 comma 4, 4 comma 3. You keep your order reverse G circle F whole inverse as it is. Next, F inverse circle G inverse. Let us write the order pairs of F inverse circle G inverse. Now, in F inverse circle G inverse, what is the second function? G inverse. So always G inverse is the domain of the composite function. Already I said in theorem also. So what is J inverse? G inverse is 2. So G inverse 2 is mapped to A, and A is mapped to 1. So 2 comma 1. After G inverse, you are going to check in F inverse because it is F inverse circle G inverse. G inverse second function domain is the domain of F inverse circle G inverse, right? Next, again G inverse 4 comma B. That same B is mapped to where? 4 comma B. B is mapped to 3. Next, 1 comma C. C is mapped to 2. And 3 comma D. D is mapped to 4. See, is they are same? Yes, they are same. Therefore, G circle F whole inverse is F inverse circle G inverse. What I am trying to tell you is GF, G inverse, F inverse. These 4 compulsory. He might be giving G and F, you find F inverse and G inverse. What is G inverse and F inverse in ordered pairs? Just reverse the order. Then, suppose F is given, G inverse is given. You find F inverse and G. Whatever it is given, 4 things we want. 2 will be given always. So F, G, F inverse, G inverse. These 4 compulsory. And G inverse in ordered pairs means for G, whatever the ordered pair I am having, you reverse that ordered pair, you will get G inverse. That's all. Is it clear? So this is the thing. And with this, your functions long answers also has been done. And tomorrow I am going to start mathematical induction long answers. And that will be the last long answers chapter. Once if it is done, I will go for inverse trigonometry 4 marks. so that your matrices, addition of vectors, product of vectors, properties of triangle, and inverse trigonometry. 5 chapters, 4 marks has been covered. Is it clear? That's it. Okay. So we'll continue.